Hi, welcome to this lecture. In this lecture, we would discuss some two topics associated with calculus, which are important to understand and they would be useful in some particular context. So, first I will tell you the title and then we would explain what they are. So, there are two topics which we would quickly discuss. One is called L'Hopital's rule. L'Hopital's rule is also called L'Hospital's rule, should be read as L'Hopital's rule. And the second part is partial derivatives. These are two different topics. In this lecture, we will answer two questions. First, using the L'Hopital's rule, L'Hospital's rule, we would answer how to evaluate a function when we get things like 0 by 0. And the second question is how to find derivatives when the function has two variables. These are the two things that we would discuss in this lecture. So, first let us think of this rule called L'Hopital's rule. So, this first of all about the name a little bit I want to say. This is a person's name. It's called Guillaume L'Hopital is the person's name. It's a French name, it's a French mathematician. So, a French mathematician called Guillaume L'Hopital found a rule. Often in some books is written as L'Hospital. I think it is because the L'Hopital would mean the hospital. So, this a rule by this mathematician named L'Hopital is very useful in mathematics, and that is something which is used when we have to evaluate some function at some particular point. Let us consider the function first. Let us consider the function sin x by x. So, let us think of this function f of x is sin x divided by x. Now, if you want to plot this function, for example, you would want to evaluate this function at different points. So, what is the value of the function when x is 0? This is something that you would want to think about it. So, what is when the function goes to, as x goes to 0, what is f of x? As x goes to 0, what is this f of x? This is something that you would want to know. So, in this case, if I put sin 0 by 0, sin 0 is 0, this is x is 0, so you would get 0 by 0. And 0 by 0 is indeterminate, we cannot determine what is 0 by 0 is. Therefore, because 1 by 0 is infinity, so infinity times 0, we do not know what that answer is. So, since this is indeterminate, so whenever you have such situations, sin x by x, and you want to evaluate this at x equal to 0, you would get sin 0 by 0, which is 0 by 0, which we cannot determine. There will be some other examples, like many other examples, you could think of many other function, like a simple function you could think of, for example, x square minus 25 divided by x minus 5. This is some function that you have, f of x. When x is in the limit, x is going to 5, in the limit x is going to 5, in the limit x going towards 5, x square minus 25 divided by x minus 25, x minus 5 would be, so x square is 25, 25 minus 25 is 0, x minus 5 is also 0, so you would get 0 by 0. So, whenever we have such 0 by 0, this is indeterminate. Sometimes you would also get infinity by infinity. This is also indeterminate, but of course 1 by infinity can write 0 as, so this is essentially, so this is also like indeterminate. So, whenever you have such indeterminate quantities, we have to use a rule prescribed by this French mathematician called Guillaume de L'Hopital. So, whenever we have function giving indeterminate, when the function is indeterminate, in situation, right, in indeterminate case, use a rule which is called the L'Hopital rule, L'Hopital's rule. And what is the rule? I am going to describe what is the rule. So, rule, let us take the example of sin x by x. So, what we want? We want to calculate sin x by x when x is 0. So, since this is sin 0 is by 0 is 0 by 0, sin 0 is 0, x is 0, this is indeterminate. So, what we want? The rule says, this is the rule, take the derivative of numerator and denominator. So, you calculate d by dx of sin x and d by dx of x, and then take the limit, and then take the limit. So, this is nothing but cos x divided by 1, and then now take the limit. Now take the limit x going to 0. So, when cos x, this is cos x, so when x going to 0 is cos 0 and this is 1. So, the answer of this sin x by x when the x going to 0, the answer is 1. So, this sin x by x in the limit x going to 0 will give us this answer which is 1, because this is the way to do is find the derivative of the numerator, find the derivative of the denominator, and then take the limit here. So, what did we do? So, we did basically limit. So, we just took the limit x going to 0 d by dx of sin x by d by dx of x, which is limit x going to 0 cos x by 1, which gave us 1. This is what we did. So, the rule, the L'Hopital rule says if, so L'Hopital rule, what does it say? So, let me write down. This would essentially say that if you have a function, if the limit x going to some a, so if limit x going to a, you have f of x by g of x. If this is indeterminate, then you take limit x going to a df by dx and dg by dx. So, you calculate the derivative of the numerator and derivative of the denominator separately, and then take the limit, and this would be the answer. Whatever we get would be the answer for this. This would be equal to limit x going to a f of x by g of x. So, this would be the answer to this question. That is what this rule would specifically say. So now let us take the other example that we just discussed. If we have x square minus 25 divided by x minus 5, and you want the limit x going to 5, and this is going to be 0 by 0, so we cannot determine. So if I take the derivative of this, derivative of the numerator, so derivative of x square is 2x and derivative of 25 is 0, and derivative of denominator is 1. Right, the derivative of denominator is 1, and you have to apply the limit x going to 5 here. This would give you 10. So the answer to this is going to be 10. As x going to 5, this value will go to 10. This function would be have a value 10. The rough idea is that how does the slope vary, how fast this goes. Slope derivative would mean slope, and how does the slope would help us to determine where it reach is what is being used. The idea is being used in this, which I would urge you to read about and think about how this can be done, what is going on while this rule is implemented, why this rule is useful and appropriate. But in this, for the purpose of course, enough to do that whenever we would use some function, we might get 0 by 0 or infinity by infinity. Immediately take the derivative of numerator, denominator, and apply the limit, you would get that function. So it is all that is what is wanted in that part. Now we would discuss the second part. This part is called partial derivatives. Concentration C, which is a function of x and t. X is space and t is time. Both the C varies, so it would vary. If I have a cell, the concentration would vary, of course, in space, but it would also vary in time. Like this is t equal to 0, in the next minute or next hour, this concentration would be more here and less here. So the concentration could change in time and along the space. So whenever you have some function, let it be concentration or anything you want, which is some function of two things, x and t, very often you would want to take the derivative only with respect to one of it. You want to keep time constant and decide how is it changing in space. So that is, think of you have a cell or you have a tube in which you have concentration, and you want to know at t equal to 3 minutes, at the third minute, how is the concentration varying along the x. That is all I want to know. I keep the time constant. I want to know how is the concentration varying along x. This quantity, this thing to write mathematically is not, if I write df by dx, it will be wrong. The way to write this is del f by del x. So this symbol like this is called the partial derivative. Partial derivative. What does that mean? It means exactly what we just said. I keep the time constant at t equal to 3 minutes. I am interested to know how is this function, how is concentration varying along the x. If the function is concentration here, how is this concentration function varying with respect to x? Keeping the time constant at 3 minutes, I just wanted to know this. So then I would calculate del f by del x. So let us think of an example. So let us say your example is, so let us take an example. So let us take f of x comma t. This function will be concentration or anything. So let us call this function as x square times t. So this is my function. Now I want to know only at a particular time how is this varying in space. So I will then do del f by del x. I would do partial derivative. What does this mean? I keep t as I imagine that t is a constant. Then I find the derivative of x square alone. This is what this means. So this would mean keep t constant and find the derivative of x square alone. So that is t times 2x. So this is 2xt. So this is what is happening. So I fix the time. This time could be 3 minutes or whatever the time, and I find the derivative of the x part only with respect to x alone, and this is called del f by del x. Same thing I could find del f by del t. So let us take the same example. I have f of x comma t, which is x square times t, and I want to calculate del f by del t. What is that equivalent in the case of concentration? What does it mean? Let us think of what does it physically mean. I have a cell at different times. I am interested what is the concentration at the center of the cell. That's all I am interested. So I will look at only one x location, and I look at the concentration here was very large at t is equal to 1 minute. At t equal to 1 minute, the concentration was large. Then it little bit reduced, and then it is further reduced. So the concentration was increasing or decreasing as the time goes. I don't know. So this is equal to 3 minutes, and so on and so forth. It could increase or decrease depending on it. So the function. So the point here is that I look at only at one particular position, but at different times. So this is time. So at different times, I look at just one location and measure the concentration there. And if I am interested, how does this change with time? So how does the concentration change at x as a function of time? Then I would do derivatives like this. In this case, if I have a function x square t, if I do del f by dt, the partial derivative with respect to t, I would assume x square is a constant, and then I would take the rest of it and find the derivative with respect to t, which is 1. So the answer is just x square. So this is very useful because we have things changing in x and t. Sometimes you would have things changing along x and y. So you would have, like, if I take a cell, very often you would have things varying both along x and y. So if I have a cell, so this is my xy axis, and if I look at in the cell, the concentration would be very small here, very high here, and small if I go. So very high here, and it could reduce and then further again increase. And also when I go x, I could reduce and then increase here, and then again reduce the small concentration, again high concentration here, and then small concentration here. So there is the concentration changes with x and y. Very often we would want to just take one particular value of x, right? So just or y. So I just want to take this particular value of y, and I want to see how the way concentration changes. It first decreases, then increases. So I want to know how does this concentration C changes with respect to x, keeping the y constant. So I want to do del C by del x, keeping y constant. So I take a y value and I look at how does the concentration change along x. I can take another y value and then I look at how does the concentration change as I go along the x-axis. So this is represented by del C by del x. Sometime you would want to have the opposite, where you would want to take some particular x value. So at this particular x value, you would want to see how does the concentration increase as I go along the y. So here I would want to calculate del C by del y. As I increase y, how does the concentration change for a particular x value? So this x value, I go along this x, so x is same, I am not varying x, but I would vary y, and I just wanted to calculate how does del c by del y, keeping x constant. So, this partial derivative, this kind of idea of partial derivative is going to be very useful both to understand things varying spatially x, y, z, and things varying temporarily, which is x, y, z, and in general x, y, z and t. So, there could be many examples. Concentration is the most studied, most useful example in biology, where concentration of proteins vary across the cell. Any heterogeneous things like in space and time, any event around us would vary both in space and time. So, that is always useful to describe any real life phenomena. Anything that we see around us would be varying in space as well as in time. So, therefore, this partial derivative is going to be very useful. Another small thing which is something that we learned, but we want to clarify something which is slightly separate, which is derivative, which is the third thing, which is derivative if you have a function which is like u by v. So, we learned if you have a function u times v and we want to calculate df by dx, we said first you keep the u constant and calculate dv by dx, then you keep the v constant and calculate du by dx. So, this is something that we discussed. Sometime you would have this function which is like a ratio of two functions. So, you have in this case, as we said, if f is u by v, then if you want to calculate df by dx, how will we do that? The idea here is, again, I do not have to learn. If you know this, you can use this same thing, because u by v I can write as u v power minus 1. So, then this became product of two terms, and if you have a product of two terms, I first keep the u constant. So, this is basically d by dx of u v inverse, which means I keep u constant and find the derivative of v inverse, plus I keep the v inverse constant and find the derivative of u. So, this would give us exactly the same idea. So, whenever you have derivative of ratio of two functions, this is the idea to use. Write it as u times v inverse and do this case. For example, let us take e power kx divided by some function. So, let us write e power minus kx divided by some other function. So, let us say x square. I am just writing some function. If this is my f of x, I would write this as e power minus kx times x power minus 2. If I have sin x divided by e power kx, if this is my f of x, I would write this as sin x e power minus kx, and then I will find the derivative of this. So, if I want to find the derivative of this df by dx, I would keep sin x constant and find the derivative of e power minus kx, which is minus k e power minus kx. Then I would take e power minus kx constant and find the derivative of this, which is cos kx times k. So, I would do this kind of thing and solve this. So, 3 things we learned, these are 3 miscellaneous things. First thing we learned is L'Hopital's rule. So, let us summarize what 3 things we learned. So, 1, we learned the L'Hopital rule, which said that in the limit, if f of x by g of x is indeterminate, this is equal to limit x going to a, f prime of x, this prime means derivative, and g prime of x. So, you take 2 derivatives and then you apply the limit. This would be equal whenever there is these are 0 by 0 or infinity by infinity. That is the first thing we said. That second thing, that if you have some function x comma t, you can calculate del f by del x or del f by del t. These are called partial derivatives. And the third thing is said that if you have f is equal to u by v, then you can write it as u v inverse and then calculate the derivatives of this u inverse v. So, these are the 3 things I want to say, which is very useful in the lessons ahead, and we would use these ideas very often. With this, I would stop this lecture and continue in the next class. Bye.